So I'm back from a trip and I want to do a bunch of review. I decided to start with 3 questions that would be kind of representative of the easy stuff from vectors. So if I had the vector 2, -3, and just to make it more clear, you can start any vector anywhere you want. But if you start this one at 0, 0, would you draw me this vector? Okay, so number 1 is just draw the vector 2, -3. And since you get to start anywhere you want on a vector, as long as it's got the right direction and the right magnitude, which is like the length of it, I like to start them at 0, 0 if I have a choice. Okay, so number 2 will be what is the magnitude? And so if this is vector v, then if I do this thing, that means the magnitude of v. Basically, that means the size of it. So once you got it drawn, it shouldn't be too hard to find the size of it. Number 3, again, totally on the easy side here, is that if I gave you this equation, I'd like to know what the point is that it starts at by giving me your classic TXY chart. You should be able to tell me a point that it starts at and another point that's on this line, just using the classic TXY. We'll see how well you remember these things. Again, not going in the grade book, but you're human. It's a Monday too. You forgot some stuff over the weekend. As long as you have 2 out of 3 and you're not completely lost on the other one, I'd feel okay about these. Okay, let's see how you did. So first of all, to draw 2, -3, you can start anywhere, and then you got to go 2 to the right. And then the -3 means down 3. So that's like to there. And remember that vectors aren't a dot. Vectors are an arrow that's going to a spot. Okay, and it's not really about exactly where it started or where it ended. It's that it's got direction and magnitude, and that's the direction, and the magnitude is the length, and that's the next part. So to do that, you can just label this and say, well, that's like 3, and that's like 2. And so then, well, how long is this last side? Well, it's square root of, and then you square them both, so 9 and 4, and since you're getting the longest side in a right triangle, you add them together, so square root of 13. Raise your hand if you had. Square root of 13, awesome. And then last but not least, if you're looking at this, that's a point. If you did not know that, maybe you should take notes on this. And this is the vector, and they are different. Okay, so when it's written in this form, they're giving you a starting point, and they're telling you to move in those directions. How far in those directions? Well, do you want to do 1 set of it, or maybe 2 sets of moves in that direction, or 3 sets of moves in that direction? You can even put a -1 in there, and kind of like thinking of it as going back in time. All right, so you can put in anything you want for t there. All right, so I suggested you give me 2 points. The one where it started, well, that was easy, because if you understood this, it started at 2, 4. But that would be at t is 0. It was at 2 and 4. Okay, because if you have a 0 here, to 0 out the 1, 5. All right, and then I would have just put in a 1. And then you're putting a 1 here. And then you have 2 plus 1 times 1 for this. And that makes 3 for your x value. And then your y value would be these 4 plus 1 times 5. And that'll be 9. There you go. Raise your hand if you were on track on those. Okay, good. Question?
So this, in this form, in the vector form, it's the graph of a line?
It is, it's a lot like a line that started at this point and goes with that slope. It's a lot like a line.
So it's a array?
It does go in both directions though. So it does start here, but because you can use t can be a negative, it's more like a parametric that can move. It's a little different than a parametric. That's the next level question, is about parametrics. So how about if we just move on? Yes, this is a line, yes. But is it array? No, because it doesn't just start in one spot and go in one direction. It can go in either direction from that spot.
So this point is just part of the line?
This point is part of the line, yes. All right, so now we're going to take that same point. I'm just going to rewrite it so you can see it easier. That same line here, 2, 4, plus t times 1, 5. And do you remember multiplying this out and making a set of parametrics out of this? Because this is not in parametric form, but I can make it be in parametric form. If you remember that, that's a next level skill. I'm going to call that question 4. Try to make that into parametric. I'm going to pause for a minute while I give you some time to work on that. Okay. If you knew what you were doing, this was pretty easy. For parametrics, you want an x equation and a y equation, right? So the x equation, not too surprising to me anyway, is these top numbers. But you have to throw in the t also, of course. So 2 plus 1 times t, or just t. And then for the bottom equation, you need a y equation that has t in it, right? So then I got this, y equals 4 plus 5t. Now, what do you need for a parametric that I don't have yet, Mr. T? Do you remember?
No.
Okay.
Oh wait, do you need a limit?
Yes, you do. So the limit needs to go between, but I just got done saying a second ago that this thing isn't limited to only starting at 2, 4. You know what I mean? Because you can go in any direction. It is headed in this direction if you just put in positive numbers, like for t. Then it would start at 2, 4 and then move in this direction. Okay, but I'm going to say that this goes from negative infinity to infinity because I don't have any specific spot I want it to start and end. Okay, next, what if I wanted to turn it into, do you remember this? This is from last unit, parametrics, change to rectangular. What's different about parametrics and rectangular? For rectangular, you don't want the t in there anymore. Would everybody please make that into rectangular? We made it parametric by making it have an x equation and a y equation. Now we're making it rectangular by getting the t out of there. If you're doing this, t equals x minus 2, you're on the right track. Now you can solve them both for t and then set them equal, or another way I showed you was you can take this, since t is x minus 2, and stick it right there and replace the t with x minus 2. So I have y equals 4 plus 5 times, instead of the t, x minus 2. And again, I could have solved this one for t and set them equal, and I would have got the same thing if I solved it for y. The nice part, it is solved for y this way, so that's kind of nice. Should I simplify it further? I certainly can. 5x, and then that's negative 10, and the plus 4 makes negative 6. Okay, so that's something we could expect you to do on the test, is to change things from the original form here, which was, let me look at it, vector, into parametrics, and then from parametrics into rectangular. All right, so that's a kind of an intense question. Here's number 5. you got two vectors. I'm going to call it vector V. That was a good name for a vector. And vector P. And if I tell you that vector V is this, 2, 3, 5, and I have another vector, 4, 0, -1, those two vectors, you can add them. It's as simple as you think. You just add the top number, add the middle numbers, add the bottom numbers. Okay, but you can also do a dot product of them. Do you remember the dot product? That was a new thing. Well, it was near the end of the unit that I was gone for. So this is, I'm going to just, instead of putting a dot in there, because then the kids are like, do you mean times or do you mean dot product? I'm going to just write the word dot. Now, dot product is used when you want to find the angle between the two vectors. If you wanted to see this, you'd have to graph it and go, okay, this one is going in this direction. I always start them at 0, 0. And then it's going 2 to the right, up 3, and then out towards you 5. You got it in your head. Imagine that that dot is coming towards you 5, and then you have a little arrow tip that connects it, except it has to be coming out at you in 3D. This would be the part would be really cool to have 3D goggles for everybody to see that in 3D. Okay. But that's the direction this first one is going. And then this other one would be going, again, I could try to draw it in 3D. It's going to be really hard, but I'm going to just kind of give you the general idea. I go over 4, up 0, and then, so that'd be kind of like this, except it would be heading back away from us, and it'd be an arrow like that. It's like this, except it's headed that other direction, and then it's the angle between those two. To get the angle between those two, we'll need the dot product. Would you just figure out the dot product first? And then I'll ask you to remember for question 6, what is the angle between them? Hint, it involves cosine. There's a little formula that I asked you to memorize, and I get you might not have. It'd be easy to forget, but it involves cosine and it involves the dot product. All right, so here's the dot product part. You just have to multiply this times this. 4 times 2 is 8. That times that. 3 times 0 is 0. And that times that. 5 times -1 is -5. And then I add all of them. So dot product is a weird mixture of multiply and add. And I get 3. Can anybody else verify they had a dot product of 3? Cool. Do you remember the special thing about dot product being 0? If the dot product is 0, then what? Anybody remember? Yep.
It's perpendicular.
Yes. The two little arrows, which are like what a vector's like an arrow, those two arrows would be perpendicular. Everything I'm telling you is important, of course. So if you're trying to get ready for this next test, this is a great page of like, more than normal on this test, you could brush up right before the test with things like this. Like, what is that little thing about the dot product being 0? Oh, it means that the two things are perpendicular. And then what is that little formula for finding the angle? It involves cosine again. Anybody got this? Anya. Let's try Anya this time.
Okay, so the dot product of A and B is equal to magnitude of A times
Okay, so let's do it in this context. We have a V and a P. Okay, so let's use V and P. So I'm going to do V dot, and I like to put a dot with the word dot, but you can put a dot. I'll accept that. And I'm dotting the regular vectors, not the magnitudes. So here's my regular vectors. I'm just dotting this vector and that vector, which we just did. and we got 3. Okay, and then what?
Is equal to magnitude of v.
Magnitude of V. I'm putting the bars around it, and that means magnitude. Do you guys remember that? That the absolute value means like magnitude of? Okay. Keep going.
Times magnitude of p.
And notice that's a times, not a dot product. Magnitude of P. So one side you got the dot. The other side you got the multiply of the magnitudes. All right, and then
Times cosine of the angle between the vectors.
cosine of theta. Very good. That is the key formula. So on the one side it's a dot, on the other side it's a multiply, and you got to know the difference. The dot product we just did above here, and we got 3, so I'm just going to bring that on down, and I get 3 equals the magnitude of V. To do that, if I drew a picture for you, it'd be really hard because it's in 3D, but it's the length of the line, kind of like this. Length of these lines. So how do you get them? It's the square root of this squared, and this squared. So 2 squared is 4, 3 squared is 9, and 5 squared is 25. So then the V magnitude ends up being 13, 30, I think 38. Can anybody verify square root of 38? Okay, cool. Times the other one, which would be square root of, and it's 4 squared and 0 squared and negative 1 squared. That was easier. So 16 and 1 is 17. And that's a multiply. So if I had a calculator, I'd go 38 times 17 and say it's the square root of that. And then cosine theta. Then I'm going to divide both sides by the root 38. I'm going to keep my life simple and just keep them in separate square roots because I don't know what 38 times 17 is. Square root of 38, square root of 17. Those cancel. And then how do you get theta alone? How do you get cosine off of there? What's the opposite of cosine? Inverse cosine. So you do inverse cosine of 3 over root 38 root 17. And there is an answer in exact form. Because that would have been a weird decimal. It would have gone on forever and we would have had to round it anyways. This is actually more accurate than giving the decimal. Yes?
So is multiplication is different from the dot product?
Definitely. We don't multiply vectors by themselves. We multiply their magnitudes. Okay? So we don't multiply vectors at all. And I just want to make you, I don't want you to say that dot product is multiplying vectors because it's not. It's a weird mix of things. It's a multiply and add. Okay? So we don't multiply them. All we do, we can add vectors. That's easy. You just add the top numbers, the middle numbers, and the bottom numbers. But we don't multiply them. But we can multiply their magnitudes. Okay. So when the kid comes up and asks, is this multiply or dot product on a test, I can tell you if the question, is saying that to do the dot product versus, but they're both dots. But we're not going to be multiplying vectors, but we could be multiplying their magnitudes. Okay? But we can definitely do dot products of vectors, and it's kind of like multiplying them. All right, cool. There's a good review of the stuff that I would have wanted you to know up to here. It's not everything, but it's most of the things. And then the last thing I got to get you through is if you have two equations, okay, like let's say x, y, z, write these out for me. 1, 2, 3 is a starting point, plus t times 4, 7, 0. Do you get that that's an equation of a line that starts here and goes in that direction, but by using negative time, it can also go in the opposite direction, but it's just one straight line in 3D space. Okay. Now, here's another equation. x1, y1, and z1 And I'm going to have it start at 4, 9, 3. And I'm going to use a different thing. Instead of t, I'm going to use lambda. For 2, -2. So the question would be, are these two vectors, like they're lines in space? I want to show you this in the classroom. Kids that are watching the video at home, sorry I don't have a visualization for you of this, but I'm going to hold up 2 meter sticks, or maybe just a couple of straight things, because I can't seem to find meter sticks right now. Anyway, so this is like a vector that is going in a certain direction. If I go like this, now it's a different direction. Now it's a different direction. Now it's a different direction. There's almost infinite directions because we're in 3D space. Okay? But it's got a length, right? That's its magnitude. Now this one over here is a shorter one. Now these, if I want them, since I can move vectors around in space, and it doesn't, like, it would change the equation of it, but it doesn't change the actual vector part. Remember, this part here is the vector. This part here is just a point. Okay, so this part here is the vector. This part here is just a point. Okay, now do they start at the same exact spot? It's a simple question. Is this exactly the same as that? No, they don't start in the same spot. Okay, but do they ever go through the same spot? That is a different question. Now, I could have vectors that go through the same spot but at different times. Okay, so imagine an intersection with some cars. Okay, so imagine we have the intersection of 101, which runs north-south, and Highway 7, which runs east-west. Do you get that there are cars flying through this intersection all the time where they would have been in the exact same spot as each other, but they're not there at the exact same time as each other? You see what I mean by that? There's a spot in 3D space where millions of people have been, but they just aren't there at the exact same time as each other. See, that's if you're occupying the exact same space at the exact same time, like right there, that's called a collision. Because if I'm there and you're there, then we're both there and we just hit. Okay? But yet, there's spots on Highway 7 and 101 that have had probably multi-millions of people in those spots. It's just they're not there at the same exact second, same exact time. Okay, so that's the difference between crossing and colliding. Intersecting means that they touch, but because vectors have an element of, like, you are going from the one place to the other, these two vectors that I just drew, they for sure intersect, because look, they crossed. The blue one and the red one, they crossed. But did they collide? Means, were they there at the exact same time? Okay, so now, somebody by now has probably figured out that these two vectors do intersect. One way you could tell if they wouldn't intersect is if they have different slopes. Do you get, if you have different slopes? No, I shouldn't say it that way. If they had the same slope, you might be like, what, the slope? This is like the slope. If they have the same vector, if they're going in the exact same direction as each other, there's a chance that they could be doing that direction, but not in the same space as each other. As in, it's like having two lines that have the same slope, and you get out of their parallel if they have the same slope. If they're going in the same direction, these two are going in the same direction. I'm holding them up in the room right now. They're both going in the same direction. So then, therefore, Will they ever touch? No, unless they are on top of each other. Do you get, if I ended up giving you the exact same vector, just that it was at a different starting point, they were going, if these two numbers were the same, if I made it 470 here and it was also 470 there, then they cannot be touching unless they are on top of each other. Okay, it's like the same thing with lines. You can have two lines that are, if you say they're parallel, you can say parallel lines never touch unless they are the same line. And then they're always touching because they're on top of each other. Okay, so the parallel lines still never touch unless they are the same exact line. All right, so you can tell I use different things. I use 470 and I use 4, 2, -2. They clearly don't have the same slope. So does that automatically mean, if I make these have different slopes as each other, it's like slopes, do you get that that doesn't mean that they touch? When they were in two dimensions, two-dimensional lines that had different slopes had to touch. I don't know if you ever thought of that, but straight lines that were on a plane, if they were just only two-dimensional, if they weren't the same slope, they were going to touch. Well, now, not in 3D. In 3D, you can be at this slope, and they'll just never touch. Okay, so is it possible that you can make them intersect but not collide? Yeah, remember the highway happening right now on Highway 7. Just a second ago, people were flying through the intersection one way, and then the light changes, now they're going the other way, and people are occupying the same exact space, just not at the same time. If they ever try to occupy the same space at the same time, that would be collide. So these might intersect but not collide, or they might just intersect and not collide. I'd like you to look at them and play with them a little bit. Hint, find a TXY chart and just in your head, like think about whether these two ever touch the same exact spot. Now this other one is technically a lambda XY chart, but lambda and t are both kind of like the counter. They're like time. The easiest point is just the point that it starts at. So the first one, at time 0. Oh, I need x, y, and z. Oopsie. At time 0, this one's at 1, 2, 3. And at time 0, this one's at 4, 9, 3. So far, do we have any evidence that they touched? Nope. But you might have found something.
If you look at the z values and you, so the first one, if you add 0, you'll see it at 3. And then if you add a 1 to it, it'll be 5, 9, 3. So but then if you change anything, if you add any value for lambda, then the bottom one will not become 3. And the top one can only be 3, so they won't intersect.
And they'll never intersect. Is that what you're saying? All right. Now, I can't expect you all to, like, he understood what he just told you, and he wasn't wrong, but it's hard to explain that. So I need to give you a way that you could always see if these two things touch. Now to do that, I think it would be good to go off and say, how would we do this if this was a normal equation? Like, what if we just had y equals 2x plus 3, and we had y equals, let me think. Five x plus 6. All right. Do those two ever touch? I know they do because they don't have the same slope. And these two are just in 2 dimensions. So that means they have to touch. You know what I'm saying? How would we figure out where they touch? So forget all about this complicated vector stuff. Just back to this. How would we figure out where those two touch? Any thoughts? Yes. So since this has to equal that, we can just put 2x plus 3 has to equal 5x plus 6. And we basically just get it down to just one variable, and then we can solve, right? Another way we could have done that is, you think of it as substitution and say, wherever I see y, I'm going to put 2x plus 3. Boop. Putting the 2x plus 3 right there. See, now I got an equation. Now I can solve it. Okay, so now I'm going to subtract 2x from both sides. And I get 3 equals 3x plus 6. Now I'm going to subtract 6 from both sides. Negative 3 equals 3x. What's x equal? Negative 1. Is that the spot where they intersected? Well, it's one of the parts of the spot where they intersected. But do you get I actually have to find the other spot? X equals 1 and y equals, well, I'm not sure, but I can go stick it back in the equation. If x is negative 1, I put it here. And then this could be y equals negative 5 plus 6. That'd be 1. So I believe I did that right. Can anybody verify that? Okay, so negative 1, 1 is the spot where those two intersected. Now, these don't have the cool element of time. Did they hit the same spot? Did they hit it at the same time? We don't do that when we are doing that system with just rectangular. We don't care when a line is in a certain spot. It's always there. When you graph the line, it goes through this spot or it doesn't. Okay, so those two both go through this spot. So that's just about intersecting. But if they did it at the same time, then they would be colliding vectors. All right, so I got to get to this one and say, I'd like somebody to look at this and change one number, and we can make these two intersect. Now, the easy way to do it, that would be so easy, would be to just change this point and have them both start at the exact same point. If they start at the same point, then duh, they obviously go through the same point. So that's a little too easy. But can you change one number in this set of equations, the blue one and the red one, to make it so they would touch? Sam?
You change the first number on the blue point to 0.
So the 4?
No, the 1.
Oh, the starting point?
Yeah.
Okay, so
1 to 0.
you're saying if I make this be a 0, that now they will be able to hit the same spot at some time. Not necessarily at the same time, but at some time. All right, I bet he's right. So would you please change that to a 0, which means that our point is now 0, 2, 3 here. So far, it doesn't really look like they're intersecting because I got 0, 2, 3 as one of my points, and my other point is 4, 9, 3. But I bet you, if you go out 1, make T1, you might see something happen. Or if that doesn't work, maybe you should try T as negative 1. All right, so everybody find another point on the blue one, find another point on the red one. So tomorrow we're going to have a little quiz. We didn't have the quiz today. I just threw you the questions, showed you how to do them. But tomorrow we're actually going to have a little quiz. Counts in the formative. Okay, I'll keep it small. Last time we did this, it was out of 7 points, and I put it in the grade book out of 6. So people that got 7 out of 7 actually got 7 out of 6. Okay, so I won't be too harsh, but we need to practice this before the test. The test is coming on Friday. So I hope that'll help to motivate you to try extra hard on reviewing tonight. And the last thing I got to get you through is this is going to be two that intersect, but how do you do collide? Well, let's just intersect, but at the same time. Like if time is 0, they're both in the same spot. All right, so when you put in a 1 here, then that meant we put a 1 here. So then we got 0 plus 4 is 4. 2 plus 7 is 9. And 3 plus, putting in a 1 again right here. But 1 times 0 is 0, it would give me 3. And look at that. See how they were at the same exact place? Were they there at the same time? No, because this is our timer. And this was at time 1, and this was at time 0. That's like two cars going through the intersection of 3D space at a certain spot, but they aren't there at the same time. All right. Now, how could you have solved this? Now, we just stuck a few numbers in, and we found a couple that worked. That is not how you would normally solve them. The way you would normally solve them is to write 3 little equations for it. Okay, so this blue one, oops, x equals 0 plus 4t. Do you see where I just got that from? Make sense? Would you please make the other two? Y equals, and z equals. Y equaled 2 plus 7t, and z is 3 plus 0. I'm going to put plus 0t, even though it is just z equals 3. Because 0t is just disappears. It's just z equals 3. Now I'm going to make them all black just to make a point here. There's the black equations that came from the blue. And now I'm going to make my red equations come from the red. So I'm going to use these down here. And I'm going to write them right next to each other. X equals 4 plus 4 lambda. Y equals 9 plus 2 lambda. And z equals 3. And I'm going to say, instead of saying plus minus, I'm just going to say minus 2 lambda. Now, since I set them up right across from each other, can you see that that has to equal that because they're both x's? If x equals the one and x equals the other, then 4t must equal 4 plus 4 lambda. Now you might feel like, okay, that's great, Mr. Server, but you haven't actually solved it. You don't know what t is and you don't know what lambda is. You're right. But I'm going to have a system of 3 equations and 3 variables, and you can solve that. A system with 2 equations and 2 variables, you can solve that. So this is going to be a system of 3 equations. Now here's the middle one. That equals that. And that's just 2 plus 7t equals 9 plus 2 lambda And in fact, do you get, I really only have two variables here and I have two equations and that's all I really need. But you could be deceived into thinking you've got the answer right if you didn't check it in your third equation, which is this one. It's one of those weird things where you can feel like you've got it, but if you don't check that last one, it could be deceiving you. Now, we're not often going to try to deceive you, but this last one's pretty slick because the 0t drops out, so it's just 3 equals 3 minus 2 lambda, and oh my gosh, that's the best one of them all. Because that one can be solved for lambda. You get how that one's just only got one variable in it? The z equation turned out to be the best of them all. Once I know what lambda is from this, I can go stick it in here. And then if I find the system by using two of my three equations, if I find the answer, and I say, oh, the answer is this, I'll be finding this exact spot like this. I'll be like, oh, the answer's 4 and 9 and 3. See, we did it this other way, but all right. Now, we did change, yeah, that's it. If I solve this system by using normal solving systems of equations, just use substitution. Once I know that lambda, heck, I'll do it. I'm going to subtract 3 from both sides. 0 equals negative 2 lambda. So lambda has to equal 0. And look, lambda equaled 0. And now that I know lambda equals 0, I can go stick that into one of these other two equations. Like I could stick it right here. If lambda equals 0, then cool, that's a 0. And 4t equals 4. If 4t equals 4, then t must equal 1. And yay, t equaled 1. So then you need to verify that actually works by sticking it in the third equation and make sure that when you stick in t equals 1 and lambda equals 0, that it actually works, and it does. When I put a 1 here and a 0 there, it actually worked. So there is writing a system of equations with three, actually all I really had was two variables, and I had three equations, more equations than I even needed to be able to solve that system. All right, there. Now, believe it or not, I've covered everything that could be on the test that's on Friday. So what do you think we're doing Tuesday, Wednesday, and Thursday? A whole lot of reviewing. But there's a little quiz tomorrow. Okay, so do your homework. I'm going to go show you some homework that I would do if I were you. Okay, on this one, I would do 4b but not d, so cross that one off. On this page, I would write x, y over the r because I think it's way easier to do the problem if you say that's an xy instead of an r equals. Because then you can have your nice little equation, x equals 7 plus negative 3, and that's called technically a mu. If you want to change that mu to a different letter like an x or a t, I personally would use t a lot and I'd use lambda a lot for this unit. But this mu is fine. It's just, they're trying to show you it doesn't have to be a certain letter. Okay, on this one, I call it Cartesian. This is also AKA just x and y. You got to get it down to just x's and y, which we also called rectangular. Okay, so rectangular and Cartesian are the same exact thing. And yes, you should know how to do this. These would be good to practice. We do this on the test. So I do those. On this one, don't feel like this is as important. We're just going to cross off that whole page. And once again, on this page, let's just do one of the two. And let's change this to an x and a y. It's so much easier than making that one letter. And then I would try number 8. You're trying to find where they intersect. That's the thing I just taught you, and super critical that you practice it. This is a little too deep, and that's what we're going to do tomorrow. Is I'm going to teach you how to do problems like this, which is they intersect, but do they intersect at the same time? It really isn't that much more. It's like just you find the intersection spot, and then you just check and see, did it happen at the same time? It's still finding the intersection spot. So we'll practice that more tomorrow. That's the only thing I have to do tomorrow besides giving you that little quiz. All right, do your homework so the quiz comes out better tomorrow. Okay, if you can catch up tonight and you get all in a good spot tonight, then you're going to be fine on Friday when the big show comes. So just a little extra study tonight. And then the rest of this week won't be that bad, and we'll end with our last normal test this Friday. Then we do have a final, of course, but we'll do a lot of review before the final. So it's only of this semester. All right, that's all I got for you for today.